Hello and welcome to the MOOC on optical communications. In this module we will continue the discussion of spontaneous and stimulated emissions and then talk about when we can get laser oscillations. Okay. So, to do that we will first start by looking at in a matter, in an active material, what is the spontaneous emission, right, how much exactly is the spontaneous emission dominating over the stimulated emission. So, let us do that. R spontaneous to R stimulated, we had in the previous module shown that this would be equal to e to the power h bar omega by kT minus 1. So, if you fix temperature, h bar is anyway fixed, k is Boltzmann constant, that is also fixed, what is left is the frequency omega. So, as you change the frequency omega, you might end up with a situation where h bar omega will be larger than kT. If that happens, if h bar omega is larger and if it is much larger than kT, then this quantity on the right hand side will be larger than 1, which means that spontaneous emission will be larger than stimulated emission. Okay. So, let us put some numbers so that this is into perspective. So, T is equal to 300 K is good enough for a room temperature value, and then put the small k, which is Boltzmann constant, is 1.38 into 10 to the power minus 23, and I also know that h bar is h divided by 2 pi, h itself is 6.626 into 10 to the power minus 34. Okay. I am not writing the units, you can just refer to the units elsewhere, and divided by 2 pi would be divide this fellow by 2 pi, and let us assume that the radiation we are interested is actually radiating at 700 nanometer. Okay. We want to know what is the spontaneous emission at frequency corresponding to wavelength of 700 nanometer. This 700 nanometer would correspond to a frequency of roughly 10 to the power 15 radian per second. So, forgetting all this 6.26 by 2 pi, 1.38 and everything, if you substitute these numbers into that expression, use a nice calculator which has scientific notation and calculate, this ratio turns out for 700 nanometer wavelength, this ratio turns out to be very close to 10 to the power 29. Okay. You can see that in an ordinary matter, the spontaneous emission is so dominant over the stimulated emission that you essentially get no light at all. There is nothing to basically stimulate and generate a laser oscillation. So, if you simply take such an active material, could be a helium neon or could be a ruby or could be another material, could be carbon dioxide, right, and then simply connect up something and then keep hoping that it is going to it is going to oscillate, you would never find that it is oscillating, simply because the spontaneous emission in this material is so dominant over the stimulated emission. So, if you do not want this one to dominate over the stimulated emission, if you want the stimulated emission to dominate, you want to invert this particular relationship in the sense that the stimulated emission must become larger, okay, and stimulated emission can become larger once N2 becomes larger than N1. Okay. When N2 becomes larger than N1, then one can actually have stimulated emission dominating the spontaneous emission. This phenomenon where N2 is larger than N1, if you recall, is known as population inversion. Okay. You can see that this is called as population inversion. Okay. Strictly speaking, population inversion does not happen in a 2-level lasers. Okay. You actually need to have a 3-level laser. First, atoms have to be somehow brought into the 3rd level, from 3rd level they have to go to the 2nd level, and population inversion is created between these 2 levels, level 1 and level 2. Okay. So, it is created between level 1 and level 2, but this extra level 3 is needed in order to mediate or make this population inversion happen. Okay. But once the population inversion has happened, you can consider only these 2 levels and then talk about a 2-level system. Okay. So, we will not worry about this 3rd level and everything at this point, we will simply assume that population inversion has happened. Okay. The question is just population inversion sufficient for us to generate oscillations? The answer is no, because stimulated emission might be happening, but then someone has to keep sending in those input photons, right. So, maybe by luck you had one photon coming in and you had a nice stimulated emission which will last for some time, but if you do not feed that stimulated emission back into the system, it will not sustain itself. So, for sustaining the oscillations, not just oscillations for a very brief period of time, you want the oscillations to sustain, only then you are actually making a source, correct. So, to make these oscillations sustain or to sustain these oscillations, you have to provide a feedback mechanism. So, any laser, most typical lasers actually have three ingredients. One ingredient is a pumping mechanism which is necessary to create population inversion. Of course, you need a material which can actually enable that population inversion. I can't take a wood and then try to create a population inversion. Okay. Some materials are easy, they can actually be able to create population inversions. Okay. And the third one is the feedback mechanism. So, any laser actually has these three requirements, and we will look at what happens when we put down all these three elements to form a laser. At this point, it might also be worthwhile to just give you the definition of a laser, or the acronym we can expand. Laser is actually an acronym. Okay. Although for the last 50 years or so, we have been talking about laser as just a noun. Okay. It actually originally meant as a acronym. This is called as, or this acronym is light amplification. Okay. Light amplification, which means that there has to be some light to begin with, and that some light to begin with comes from a spontaneous emission. Okay. Somehow by thermal agitation you have caused a spontaneous emission, photon to drop down, but then you want to sustain that photon, you want to create additional photons which are matching to that particular initial photon. Okay. So, you want to amplify the light by, not by spontaneous emission, by stimulated emission of radiation. Okay. So, this is the expansion of laser, but for all our purposes we can write laser like this. Okay. Notice the difference. If it is an abbreviation, you normally do not write it in this fashion, right. If it is a www, you want to write www, or if it is another one like say United Nations, you want to write UN, you will not find us writing like this, or you will not find writing like this. But lasers have become such commonly used word that you can write laser in this way at the beginning of the sentence, or in the middle of the sentence you can simply write this as laser. Okay. It is no longer considered to be the acronym, but it is just considered to be the noun which encapsulates a broad range of phenomenon in which light is being generated. Okay. So, the three ingredients for the laser oscillations to occur and sustain are a feedback mechanism. Feedback mechanism in optics is actually in the form of a cavity. The cavity keeps pumping things back, and then you have a pump itself. This pump could be a flash lamp in some of the lasers, or it could be an electrically pumped signal. So, you have either an optical pump or an electrically pump. The idea of pump is to basically push the atoms from N1 to N2 to create a population inversion. Okay. And then you want the material itself. So, you need an active material which can actually sustain this population inversion. So, these are essentially the three main ingredients of a laser. So, we will look at the laser oscillation. In order to look at the laser oscillation, let us assume a cavity and then dump our gain medium inside this cavity, or put the gain medium inside the cavity. Let us also assume that the cavity has a length L, okay, which we are going to measure along the z axis. Now, since this is a gain medium, that is, this medium has to provide gain, right. If I start with some optical power at the input of the cavity, so at z equal to 0, you have the power P is equal to P of 0, and then at any point along the length of the gain medium, the power there would be P of z, and this power would be equal to the power at the beginning times e to the power gz, where g stands for the gain of the medium. Assume that it is independent of the frequency, it is independent of anything else, it is kind of a constant at this point. In place of gain, if you had loss, what would be the power at this point? The power would be P of 0 e to the power minus alpha z. Okay. Since this alpha is internal to the cavity, we can write this as alpha int, just to indicate that this is an internal loss. Okay. So, you have a gain and you have a loss. The effective power of course would be P of 0 e to the power g minus alpha int times z. Clearly, if g is larger than internal losses, then this will be a larger number than P of 0 and you would obtain a net amplification. In case G is less than alpha int, this term will be less than 1. So, you will get a net attenuation or a net loss in the system, right. At Z is equal to L, these numbers in place of Z you can change this into L. Okay. Look at this equation again. I can differentiate that equation. So, I can say dP with respect to dz, and since P of 0 is a constant, that goes like that, G is a factor which comes out and then you have e to the power gz, but this is nothing but P of z itself. So, you get a nice differential equation, dP by dz is equal to G times P of z, okay, which describes the gain equation. Okay. So, how the power is actually changing in this gain medium. Okay. Now, if of course, you can also derive another equation for the loss, which is dP by dz will be equal to, in case you are only looking at the loss term, then alpha int will come out and then you still have P of 0 e to the power minus alpha int of z. So, another equation that you are going to get will be dP by dz is equal to minus alpha int times P of z. Okay. Now, let us look at what is called as a sustaining condition. Okay. We want the oscillations to sustain. Let us assume the cavity. So, I am going to redraw the cavity over here, is actually one kept at z equal to 0 and this one is kept at z equal to L, and this cavity is essentially a mirror. Okay. So, this cavity is essentially a mirror, and one can actually look at mirrors with a straight line edges, or one can have a curved mirrors, and the kind of modes that are generated will be slightly different. So, we will simply assume for simplicity now that these are straight line mirrors and they have been kept at z equal to 0 and z equal to L. We also need to specify the reflectivity of these mirrors. So, if radiation comes in from the left, hits the mirror, then a part of the light is reflected back. These are not perfect mirrors. Okay. If they were perfect mirrors, then I would not have been able to tap any energy out of them. So, they are imperfect, but their reflectivities are quite high. So, this reflectivity is R2, similarly this reflectivity is R1. Let us say for some reason the power in the form of the optical wave is travelling in this way. So, maybe it starts at the origin over here and travels all the way to the end. Okay. What would be the length over which it has travelled? A length of L. What would be the gain it would have experienced? G times L. What would be the loss? Minus alpha int times L, right. At this point there is a reflection, and R2 times input actually keeps is actually reflected back. Some power 1 minus R2 is actually escaping outside, but let us not worry about that one. The reflected power is R2, which will again travel all the way up to the input, right. At this point what will happen? There would be further reflection, right. R1 times this power would be reflected. So, one way you have a propagation of L and the effective argument in the exponent would be G minus int times L, and the other way you have another propagation through L and you get G minus alpha int into L. Here in one way you are getting a reflection R2, here you are getting a reflection R1. Okay. You imagine that the initial power is P of 0, which is the one which has been incident just at the output of the first mirror. So, that is the power there is P of 0. So, P of 0 times e to the power, so we can write down here. So, P of 0 times e to the power g minus alpha int into L times R2 would be the power that is reflected, which then propagates again as e power g minus alpha int into L and then reflects once more to give you R1. Okay. This would be the power that is. So, here you actually have an input power which is P of 0, and then after all this round trip propagation and this double reflection, you get the power which is P of 0 times this particular quantity. Of course, I can combine this and this into a single exponent, and what I get is P of 0 R1 R2 e to the power 2 times G minus alpha int into L. Now, sustaining condition or self consistency simply means that this must be equal to P of 0. If it is not equal to P of 0, if it is less than P of 0, then after about 3 or 4 more round trips, it will simply die down, because R1 and R2 are never greater than 1, okay. And if this number is less than 1, then you will not be able to get any gain. So it simply keeps dropping, eventually it goes off, right, eventually it goes to 0. So for oscillations to be sustained, it is necessary that this power must be equal to the power p of 0. From this you can cancel p of 0 and then arrive at a relation which is R1 R2 e to the power 2 g minus alpha into L must be equal to 1, okay. This is the self consistency requirement, and you need to really satisfy this particular condition. Of course, here you might also observe that you can't let g be less than alpha int, right, then it will not be satisfied up there. So you want g to be greater than alpha int. In other words, the gain of the medium has to be larger than any intrinsic losses. So one of those losses is coming from the mirrors, because mirrors are only reflecting R2 and R1. Some portion of the light is actually escaping, right. So that can be losses, but those losses are somewhat because of the mirror losses. Alpha int is the medium losses. Medium itself has some loss, and that is alpha int, and this one is the loss which is the loss due to the mirror, okay. So you can rearrange this equation to write in a slightly different form. So you can write g is equal to alpha int after taking out this exponential. So take log on both sides. So first divide this one by R1 R2 and then take the log. So if you do that one, you get e to the power 2 g minus alpha int into L is equal to 1 by R1 R2, and then if I take the log, natural log on both sides, you get 2 log, that log and exponential cancel with each other. So you get 2 g minus alpha int into L is equal to 1 by R1 R2, and then you can rearrange g now. So g can be written as internal loss plus 1 by 2 into L log of 1 by R1 R2. So you can see that the gain is getting balanced by the loss. So this is the intrinsic loss and this is the mirror loss, okay. The mirror loss is a function of R1 R2 as well as the length of the cavity L. Intrinsic loss is just the material loss, the gain medium loss, whatever that is there. For oscillations to be sustained, G must be greater than the total losses, okay. So only those particular modes which actually satisfy this condition will be sustained. Now this brings us to another question as to what exactly are these modes. Well, if you take a cavity, right, and you assume that light is going back and forth between the two, light will be sustained only when the total phase change would be an integral multiple of 2 pi. That is, if you assume that there is a monochromatic wave which can be written as e power j omega t minus beta into z, when the wave propagates through a distance, a total distance of 2L, it undergoes a phase change. It will also undergo a certain phase change upon reflection here and upon reflection here, but once after undergoing the phase changes, the wave comes goes at the right point, at the input point, you will again have to apply the self consistency result, in the sense that the total phase must be an integral multiple of 2 pi, okay. Only then this initial wave will be adding up to the new wave, and therefore this process kind of gets repeated, okay, or consistently repeated, so that the wave is actually sustained. If the phase is different, then sometimes the phase is positive, sometimes the phase is negative. On an average you will be seeing only 0, because on an average this would simply wash out, all the results are washed out. So you need a constructive interference, and for constructive interference you need a total phase change of 2 pi. So what you need is the phase change to be integral multiple of 2 pi, okay. And what is the total phase change? Phase change is given over a distance of 2L omega. So beta is the propagation constant, which can be written in terms of lambda. So you have 2 pi by lambda 0 being the operating frequency of the radiation here. So 2 pi by lambda 0 into 2L must be equal to 2 m pi. M can be 0, although because of the propagation the first number would be 1, that would be interesting, 2 and so on, okay. This further actually can be rewritten as 4 pi L by lambda 0 is equal to 2 m pi. Pi on both sides cancel, 2 on both sides will cancel here, and what you see is lambda 0 times m must be equal to 2L. This is interesting. So, what you see is that if you start with a lambda 0, if you fix the value of L, so if you fix the value of L, then the only possible modes that are going to be present are the ones which are satisfying this particular condition. Okay. So, the only ones which actually satisfy are the wavelengths that are going to exist are the ones which satisfy this particular equation. Okay. So, given two mirrors which form a cavity which are kept at a distance of 2L and a radiation whose wavelength lambda is there inside, the only possible modes are going to be this integral multiple. So, you are going to get lambda 0, you are going to get 2 lambda 0, you are going to get 3 lambda 0 and so on. Of course, you can also get 0, lambda 0 and so on, but those frequencies can be like these are the lower side frequencies, these are the upper side frequencies. But the point is that you actually get a large number of discrete modes which are all integral multiples of these particular modes. Okay. So, you get a 0, you get a minus lambda 0, you get a minus 2 lambda 0 and so on for a length of 2L. Okay. Now, there is one additional thing that happens over here. We said that this cavity contains a gain medium, right. So, this cavity contains a gain medium, and this gain medium actually consists of those two levels of energy which we talked about, 1 and 2. So, you would expect that this gain which is given by the frequency omega, right, I mean this gain medium which actually has a frequency omega or h bar omega as the energy difference between the levels 1 and 2 would, if it falls on one of these modes which are allowed by the cavity, right. So, if this frequency somehow let us say falls on this lambda 0, only that particular lambda 0 will be constructively interference and supported. All the others should in principle die out, because there is no power in other components, right. So, the energy difference is such that this omega falls only on this lambda 0 and only this particular mode is picked up. Unfortunately, that is not what happens in practice. In practice, you would see that these energy levels are not really single ones, but they are actually a band of energies. Okay. So, you actually have a band of energies, and therefore, there is actually a spread in terms of omega from the lowest point here to the highest point, the lowest point here to the lowest point in the second level. So, there is actually a spread of frequencies over which the the photons can be stimulated, emitted and absorbed. Okay. In terms of the frequencies of the cavity, what it means is that you actually have a wide spectrum of the frequencies, and if all these modes which satisfy this condition, I mean these all modes are actually sustained. Okay. So, there will actually be a mode here, there will be a mode here, and there is a mode here and a mode here. These modes are called as longitudinal modes of the cavity. Okay. And such a laser which supports multiple longitudinal modes is called as a MLM laser. An MLM laser is multiple longitudinal mode laser which supports all these modes, and the condition that G has to be greater than alpha int plus whatever the losses means that the total gain loss curve must exceed a certain threshold. Okay. And unfortunately, in this particular example which I have shown, there exists at least 3 modes, because this mode is exceeding the threshold, this fundamental mode is exceeding the threshold, and there is one more mode which is exceeding the threshold. Okay. What is the spacing between these modes? We know that the length here is T2L, and you know that time is 2L by c, where c is the speed of propagation, or in case if you are looking at a medium which has a certain refractive index, then this would be 2Ln by c or 2NL by c, right. 1 by time is frequency. So, this is c 2n into L. This is called as the modes of a cavity. Okay. So, this cavity has all these modes c, which are all spaced at c by 2n into L. Okay. The mode spacing is c by 2n into L. Okay. These 3 modes are passing the gain and threshold. So, these are going to exist in our this particular laser systems, and they constitute what is called as a MLM laser. However, most sophisticated lasers that are used for optical communications do not have so many multiple longitudinal modes. There are special mechanisms that are made to suppress these additional modes. One of those mechanisms is to actually incorporate a resonant cavity or put a filter inside, which will then select only one particular mode here. Okay. So, such a action of that one results in what is called as a SLM laser. SLM stands for single longitudinal mode. Okay. You can kind of suppress all these additional longitudinal modes and then have only the single longitudinal mode. Okay. So, this completes our understanding of the resonators and the associated laser oscillations. Just to reiterate, it is necessary that you need to have a cavity, but the moment you have a cavity with R1 and R2 as the reflectivities, there is going to be some mirror losses, plus the gain medium has some intrinsic losses. To overcome that gain, the losses, one has to have gain, and gain comes from stimulated emission. Okay. Gain comes from stimulated emission, but to cause stimulated emission you need a pump. So, the pump causes population inversion, which then causes gain, and the gain has to be greater than the threshold, gain has to be greater than the losses, and the gain minus the threshold point at which it exactly happens is called as the threshold. Okay. So, this is a way in a general laser would operate. We will then in the next class, in the next module, we will specialize ourselves to semiconductor lasers. Okay. The discussion will be quite brief because we do not want to get into too much of details of semiconductor lasers. So, we will get into semiconductor lasers in as much detail as required, and then quickly after that move on to considering optical communication systems again. Thank you very much.